I asked ChatGPT who I should invite to explain green tea, it just gave one answer. It said that I should invite my very good friends, and as I can now officially say, the friend of the Go Devroom, Jesús again. And he gladly accepted. And he even came up with an actual presentation of a gopher sitting in a race car drinking some green tea. So give a round of applause.
Okay, perfect. Thank you. Well, welcome to Brewed for Speed. This is a talk about the new green tea or garbage collector. So let me introduce myself a bit. I'm software engineer at ONA, that is an AI agent in the cloud. I'm an open source enthusiast and contributor. I really love open source. This is why FOSDEM is probably my favorite conference in the world. I'm a big fan of deep knowledge, of understanding things, how things work under the hood. Also a book author. I wrote Modern REST API Development in Go, but recently I started a blog about how things work under the hood. So if you, well, there's a series of posts about the compiler, another one about Postgres. I'm going to write another about file systems and about the Go runtime very soon. So yeah, that's me. We are going to talk here about the new green tea garbage collector. But for that, I want to start explaining how the current garbage collector, the garbage collector that is in the 1.25 version, is it works. And then I'm going to talk a bit about the memory allocator, because I think it's interesting for understanding better how the green tea garbage collector works. And then I'm going to get into the real innovation behind the green tea garbage collector. Well, as always, this is something that I'm not in the Go team or something like that. I just learned this by reading the code, exploring things, reading the documentation, all that stuff. So doing my investigation, doing my homework. So there's some simplifications or oversimplification on certain things, but I think it explains more or less how it works. So let's jump into the Go classic garbage collector, the one that is in the 1.25 version. The Go garbage collector, it's not super special in that sense. It's a regular mark and sweep garbage collector. It's a technique that is used in many other garbage collectors. The technique in mark and sweep is finding all the root objects, all the objects that are truly accessible for sure, because they are global variables, for example, and start exploring them and finding and tracing objects, finding what objects point to another objects, etc., and marking them. And whenever you finish marking everything, whatever isn't being reached, whatever isn't being marked, it's unreachable, so you can swipe that. So that's a mark and sweep algorithm. Let's see here. This is an example of how it will work. The first thing is those root objects. Those root objects come from global variables and the stack of the Go routines. So it is going to scan the stacks of all the Go routines, it scans all the global variables, and try to find objects that points to something. And for example, imagine that we have two alive root objects and they have two pointers. So it's going to say, oh, I have two objects here that I have to scan. Because I need to scan those objects, and can be many, what I'm going to do is accumulate those objects in a work stack. It's important to understand that that's a stack because it's a last in, first out, and that gives the mark phase of the garbage collector certain properties. So let's trace how it goes. I found these two objects, I put those two objects in the stack. So I pick from the top of the stack, and I take that object. So I start scanning that object. While I'm scanning that object, I found this other one. So I put that in the stack and mark this as visited. It's already done. I'm done with that object. So then I have to scan another object. So I pick one from the stack, from the top of the stack, the one that I just added. So it's there. I visited that, I keep going and putting in the stack, scanning, putting in the stack, scanning, putting in the stack, scanning. It's important to see that this is a stack, and that is going to lead into a depth-first scanning. So we are moving down the path of one object, and whenever we finish with that, we go back and keep going and get all over the ramifications of that object. And whenever I reach that point where I visited that one, there's no more objects, so I'm going to go back to the stack and pick one from the top that is the second one that we found. So we go there and do all the scanning and finding the objects, putting in the stack and all that stuff. Now I reach the point where the work queue is empty, so the work stack is empty, so everything else in the memory, it's unreachable, so I can just swipe that. So this is how the mark phase of the garbage collector works. I'm going to focus on the mark phase because the GreenTea innovation, it's basically done in the mark phase. The sweeping of the unreachable objects, it's done exactly the same in both garbage collectors. So let's talk a bit about the memory allocator. The memory allocator is a piece of the runtime that decides where your data, where your variables are stored. So whenever you ask for a new, for space for a new object, it's going to ask the memory allocator, and the memory allocator is going to follow a very smart approach, actually. It's going to divide all the data in what they call M-spans. M-spans is, a memory span is just a set of pages, a set of memory pages of 8 kilobytes each that only contains objects of that size. That's not exactly true. They contain objects up to that size. They contain objects up to that size. That means that, for example, if you have an object of 22 bytes, it's going to fall in the span of 24 bytes because it's the first one that is going to be able to store that. But the pages are divided in slots of that size. So if you have a page that is part of the 24 bytes span, it's going to have a slot of 24 bytes. So everything is same size inside that page. So you can, it is easy to parallelize the things and easy to index, easy to find the things. So it's a very smart approach, and we are going to see how the GreenTea garbage collector leverage that later. So let's talk about what is the GreenTea trick here, how GreenTea it's gaining all this performance. The idea is there's some difference here. This is what we saw before with the GreenTea, with the regular, the classic garbage collector. But now what we are introducing here is those pages from the memory allocator, those pages that have very specific size. So all these objects belongs to specific pages. So those objects are all in the same size and are all well organized and well structured. Okay, so, sorry, let me go back to this. In the garbage collector, what's the problem of the garbage collector? What's the problem of the current garbage collector? The problem is whenever we start scanning with in the mark phase, we are going to go to one object, and we are going to jump into another object, and then jump into another object, and then jump into another object, and you are going to jump in all over the memory. So it's not predictable what I'm going to scan next. It's not predictable for the CPU. It's not predictable. It's not. There's no data locality on that, so I can jump all over the memory. So that is going to fight really hard against the CPU cache and the CPU pipelines. So the CPU can't leverage prediction of what you are going to read next. The CPU can't leverage the current cache that already have in the L1 cache of the CPU, so it has to go to memory. That sounds like very fast, but is compared to L1 cache is 100 times slower or something like that. It's crazy slower, and it's doing that all the time because you are jumping all over the memory. So the GreenTea trick basically is instead of scanning objects one after another, it starts scanning pages. So it starts thinking about the memory and about the memory scanning in terms of pages. So we have here our objects organized in pages. Then you have also here a couple of bitmaps. One is saying, is this object has been seen already in this page? And the other one is this object has been scanned already? And that's another thing that we are going to see how it works, because we are going to go through the process. The other thing is it's no longer a stack of objects. Now it's a queue, so last in, first out. First in, first out. It's a queue, but also it's not of objects, it's of pages. So we are, the unit of work for the new Go Garbage Collector, it's going to be per page. So let's see how it works. Imagine that I have these two root objects that I found in the root on global variables or in coroutine stacks. I found these two objects that are pointing to two objects in this page. So I just mark that objects in the page as seen and put that page in the queue. So next step, I'm going to scan that page. I scan that page. I found these two objects. I have to scan these two objects that are the ones that have been seen. So I say, oh, they are pointing to other two objects. So I mark the other two objects in the other page and put that page in the queue again. And now those objects are already scanned. So next step, I take another page. So I start scanning that page from the queue. And I found another two objects, so I mark those objects as seen in the other page and put that page in the queue and start scanning that page and so on. There's one case here where you can see that the first object in the page is pointing to the second object on the page that I already scanned, but that's okay. The GreenTea can scan again multiple pages. Can scan again the pages for finding objects that haven't been seen before. So what we are going to do is mark the scene there, and we are going to go again to that page and scan that and go there and keep going. We revisited some pages because it's needed, and we finally have no more pages in the queue, so we have scanned everything, and everything else is unreachable. Another thing that is important to understand here is because it's a queue and because it's scanning things and marking in other pages, this process is very kind of linear. I'm marking this page and then the next page and then the next page. But the reality is probably your objects are pointing to 7 different pages. So you start scanning the next page and you point to other 7 different pages and you scan the next page and other pages. And what is going to happen is it's going to accumulate seeing bits, seeing flags in those pages, and whenever you reach that page, maybe you scan in one go, you scan 70 objects or 3 objects or 7 objects or whatever number of objects, but you are going to accumulate that. So this way, the Go Garbage Collector has the advantage of scanning very localized in memory objects at one time. So it's going to go in a page and say, oh, now I have to scan 13 objects, and those 13 objects are going to be in my L1 cache. I'm going to do all very quickly because it's all fresh and I don't have to go to memory and all back and forth all the time. So that's the main innovation. So let's see how the marking work, the page checking work. Imagine that you have this sync bitmap and this scan bitmap here. So I have to scan the page. So I start looking for the first one. Is pending? No, it's not pending because it has been already scanned. Okay, the second one is pending? No, because haven't been seen yet. Is the third one pending? Yes, because has been seen but not scanned. So what I'm going to do here, this is another bitmap, is one bit that's saying, oh, the object in this position needs to be scanned. What it's going to do is going to expand that object towards It's going to do a bitmap of words. Everything is a one there. That is saying all these words, all these slots that could store a pointer is something that we can that can be a pointer. Okay, and a live pointer. So I'm scanning that. So what I do is getting this pointers map. The pointers map is saying for this object, these are the words or these are the positions that store an address. So it's going to compare that bitmap and say, oh, these are the positions in the memory that has a memory address that I have to add to the queue and all that stuff. Then I go to the next one, expand the words, compare to the pointer map, and I have another 2 pointers. So those 4 pointers points to other pages. I mark that in the pages and put that in the queue. So that is how the page checking works. But there's something else that is pretty cool, the hardware boost. So the Go garbage collector, Go GreenTea garbage collector, is using AVX 5012 instructions that are single instruction, multiple data, that are a set of instructions that allow you to parallelize certain operations at CPU level, what is pretty cool. To get some numbers, the Go GreenTea garbage collector is saying that it can save in the mark phase of the Go garbage collector between a 10% to a 40%, but with the AVX instructions, it's giving a 10% extra. The AVX instructions is only in very modern CPUs, so don't expect your 2 years laptop or something like that to be able to run these things. I don't know exactly the set of instructions, but you need to have a very specific set of instructions supported in your CPU for getting this work. But well, what it's going to do in this case is you are going to have this bitmap of seeing and scan, and instead of going, oh, let me compare this one, it's going to go in one go. So in one go it's, oh, these are the pending ones because I'm going to parallelize everything and I'm going to get the scanning there. And then I'm going to say, oh, I'm going to expand them. And you expand everything at once. It's one go for the CPU. And then you compare that with the pointers map and go there and boom, one go. So it's a 10% extra performance in the mark phase of the garbage collector. So it's a pretty good boost. There's a catch anyway. There's a catch. The Go garbage collector is, the GreenTea garbage collector, it's a great improvement in general, but there can be situations where the performance boost is not there or can even be a regression on performance. This will be kind of the case. Imagine that your data is shaped in memory in a way that every time that you scan something, it points to a new page, and that points to another page, and that points to another page, and then go back to the first page and point to another page, and end up not accumulating same objects in the same pages. It's just scanning one page at a time, or maybe 2 objects per page every single time. That is going to end up not covering the extra cost, the extra accounting that we are doing for GreenTea. In general, the expectation is a 10 to 40% improvement on the mark phase, but it's not going to be something 100% sure that it's going to happen. Some references. I really like the talk from Michael Nitzek at GopherCon. It's very good. Check it out. He is a Go developer. So he's a Go compiler, Go runtime developer, so he does a great job giving the talk. The Go dev blog, it's really good actually, as it's very deep. The Go source code is always an option to check it out. It's not the simplest code in the world, this one, so it's hard to read. One small thing, my company, Ona, it's giving away $200 per month for free for open source developers. So if you are an open source developer and you have an open source project feel free to, I'm going to leave some cards there that you can feel free to pick them and share that with other open source developers. Up to $200 per month on free credits on the AI agent. And, well, my social networks, and it's everything. You can do whatever there. And that's it.
Is it compacting?
Sorry?
Is the new garbage collector compacting?
No, it's not a compacting garbage collector. There's no movement in the memory once the object is get there. But the memory allocator helps a lot on having the memory very compact anyway. So, yep. We have time for questions?
You have 5 minutes.
Oh,
I made it 3 minutes.
I saw you come in, so...
I see one very important question. I'm quickly going to hand you the microphone for the online questions.
Yeah, thank you. I might miss it in the talk, but as I understand, I've been also reading the source code of this like optimization. It works only for small objects. So
Oh, yeah.
it's very important because technically the main like bottleneck it's allocation and deallocation of small objects. And for big objects, we still use old like strategy. And as far as I know, there is no plans to actually extend the strategy for big objects because it's not efficient.
Yeah, that's a very good point. Thank you. Actually, yes, I think the bigger object is 512 bytes or something like that. It's only for that kind of objects because at the end of the day, you have a page that is 8 kilobytes. So if you start, if you have to scan big objects, you end up going to the pages for all these accounting of the pages and all that stuff is not going to serve. Yeah, but not only that, if the locality is going to be only, the max of locality that you're going to have with that is 20 objects, tops. So it's not, the benefit is not going to be that clear. It's more focused on the small objects. Yeah, there's a very good point. Thank you.
Thank you, and because that was a good question, that's the last one for today. If you have any more garbage collecting questions, you can always invite him around the Devroom. He'll be here all day. Do you have a hallway track somewhere where you'll be?
No, but I'm going to be around, so I'm very, anybody want.
Look for him. Look for him.
Yeah.
Remember
Talk to
this
me.
guy.
Yeah.
Thank you.